In Java, the concept of a thread pool is represented using the executor service interface and its implementations. So we have thread pool executor, which is a typical thread pool implementation. This is the one that we use most of the time. We also have scheduled thread pool executor. With this, we can schedule tasks to run after a delay or periodically. For example, we can schedule a task to run 5 hours from now or every 2 hours. We also have fork join pool. This is a special type of pool that is designed to recursively split a task into smaller tasks and then combine the results of each subtask to produce the overall result. It's like a divide and conquer algorithm. Now let me show you how to create a thread pool. We have this executors class that is declared in the java.util.concurrent package. This class has a bunch of static factory methods for creating an executor service. So with these methods, we can create an instance of these implementations. Now, why shouldn't we create a new instance of thread pool executor directly? We can definitely do that, but it's a little bit difficult. Let me show you. So if we type new thread pool executor, take a look. This constructor has a bunch of parameters like core pool size, maximum pool size, keep alive time, and so on. So creating an executor explicitly is a little bit difficult. That is why we use the factory methods on the executors class. So here we can call new single thread executor. This returns an executor with a single thread, not something that we use that often. We also have new fixed thread pool. This will create a thread pool with a given number of worker threads. So that would be an instance of the thread pool executor class. We also have new scheduled thread pool. This will return an instance of the scheduled thread pool executor. Okay, so let's call new fixed thread pool with 2 worker threads. Now we'll store the result in a variable called executor. Now look at the type of this variable. That is executor service. So we're dealing with an interface here. At runtime, the type of this object is going to be thread pool executor. Let me show you. So if we print executor.getClass.getName and run the program, we see thread pool executor. That is a thread pool with a number of worker threads. Okay, so we have an executor. Now we can call executor.submit to submit a task to this thread pool. Now this method is overloaded. We can pass a runnable object. We can also pass a callable. That is a task that returns a result. We'll look at that later. So for now, let's pass a runnable object here. I'm going to use a lambda expression. So here, let's print the name of the current thread. So thread.currentThread.getName. Now technically, we don't need the braces here because we have a single print line statement, but I'm going to keep them here for clarity because I don't want to put this line over here. Otherwise, it's going to pop out of the screen. So that's all we have to do to run a task on a separate thread. If we run this program, you can see our task was executed on this thread, pool 1, thread 1. So we didn't have to explicitly create a thread. Now, if we have 1,000 tasks, we don't have to worry about creating too many threads and running out of memory. We simply submit those tasks to this executor, to this thread pool, and this pool will assign our tasks to worker threads. Let me show you. So here we have a pool with 2 threads. Let's add a for loop. For I, we start from 0 to, let's say, 10. Now, in each iteration, we submit a task to this pool. So we have only 2 threads available, but we're submitting 10 tasks. Let's see what happens. Take a look. So some tasks are being executed on thread 1, other tasks are being executed on thread 2. See? So internally, this executor maintains a queue. Every task that we submit goes in this queue and waits for an available thread. Okay? Now, let's get rid of this for loop. We don't need it anymore. So we create an executor and submit a task. Now, if I run this program again, we get this dialog box saying that our program is still running. Why is that? Because when we start an executor and submit a task, the executor thinks there might be more tasks coming in the future. So it's not going to terminate. It's going to stay in the memory waiting for new tasks. So we have to explicitly shut down an executor to terminate our program. And to do that, we call executor.shutdown. We also have shutdown now. The difference is that the shutdown method doesn't stop the current tasks, so it will wait for the completion of those tasks, but it's not going to accept any new tasks. In contrast, if we call shutdown now, this will force the existing tasks to stop, okay? So let's call the shutdown method. Now we run the program. We get this dialog box because we didn't shut down our executor previously. So let's rerun this program. All right, our program shut down. So if I run it again, we don't get that warning, okay? Now, what if something goes wrong over here? Or we might have some code, and this code throws an exception. With that, we're not going to be able to shut down an executor properly. So as a best practice, we should run this inside a try finite block. So I'm going to add a try block here. In the try block, we submit our task. And in the finite block, we shut down the executor. With this, we'll make sure that no matter what, we always shut down an executor and release it from the memory. So this is the benefit of using the executor framework. We don't have to worry about thread manipulation anymore. We let the executor framework take care of all of that. But you have to remember, even when using the executor framework, we still have to worry about the concurrency problems. So if two tasks modify an object concurrently, we're going to run into issues. So the executor framework does not protect us from the concurrency problems we talked about in the last section. It just simplifies thread manipulation.